Hello, and in this video we're going to continue talking about conditional probabilities. In the last video we established and did a couple examples of when one event depends on the other. And we said if A depends on B, then the probability of A, assuming B has already occurred, is equal to the probability of A and B both occurring divided by the probability of B. Pretty much here, B is serving as the sample space since it's already occurred, and the probability of A is equal to the probability of A and B occurring. B has already occurred, so that probability does exist, and you just divide those two since that's pretty much the probability of A over the sample space of A. So let us assume that A does not depend on B. So if A is independent of B, and remember, there was two special types of probability events, namely those that are mutually exclusive and those that are independent. So this is going to give you a mathematical way to test whether two events are independent or not. So if two events are independent, then what will we get in return? So the probability of n of A given B is equal to what? So if B has nothing to do with A, and A does not depend on anything else, then that means the probability of A given B occurred. Well, who cares about A? Who cares about B, right? So that means the probability of A given B is just equal to the probability of A. If A has nothing to do with B, i.e. they're independent. So if that is true, then that means we have the identity, well, probability of A given B is just simply the probability of A is equal to the probability of A and B occurring divided by the probability of B. So that means we get this identity by multiplying both sides by the probability of B. We get that the probability of A intersection B is equal to the probability of A times the probability of B. And some people call this the product rule for probabilities. And keep note that this is only true if A and B are independent. If they are independent, this will hold. If they are not independent, this will be false. So let us demonstrate with an example. Suppose that the likelihood of it raining is estimated to be, so probability of R is equal to 7 over 15, approximately. A local store determines that the likelihood of selling an umbrella on a given day is the probability of U equals 3 divided by 37. Now, you may be asking, does R depend on U? Actually, no, because rain doesn't care about U, right? So usually it's no. So you may also ask, does U depend on R? You may answer yes, and I probably would agree with you. But if not, then that means the probability of it raining and having an umbrella must be equal to the product of probability of R and the product of U. So that means the probability of it raining and selling an umbrella must be equal to 7/15 times 3 divided by 37. So that's going to come out to 21 over 555, which is approximately equal to 0.0378. That's if This is only if R and U are independent. And this is important. And this also gives you a tool to test whether it's independent or not. So pretty much what you can do is you can calculate experimentally the likelihood of selling an umbrella while it is raining. So you can do that, you can call it the probability of, call it the probability of star. That's the experiment, right? So once you calculate the probability of star, if rain has no effects on umbrella sales, then the probability of star should be approximately equal to the probability of R intersection U, right? Because if it has no effect, then that means they are independent of one another. Now, if rain does have effect, and sometimes people want to actually prove this, right? So this might be something you're trying to prove. That means the probability of star is not equal to or not approximately equal to the probability of R intersection U. So that means you're trying to prove that the probability of star minus the probability of R intersection U, the absolute value, is extremely large. That's what you're trying to prove. So that's pretty much like an experimental design that you can sort of prove to prove, and what does it mean to prove, independence. Because, what you're pretty much doing in that experiment is you're assuming that they're independent, and trying to prove, or trying to gain, a numerical contradiction. So let us summarize what we've talked about here. So overall, if A and B are dependent, then the probability of A given B is equal to the probability of A intersection B over the probability of B. And if A and B are independent, then the probability of A given B is just equal to the probability of A, and the probability of A intersection B is equal to the probability of A times the probability of B. So these three formulas are the most useful of them all when you're dealing with dependence and independence of events. And that's pretty much a summary of conditional probability.